All right, welcome to sections 13.8 and 13.9. In these sections, we're going to look at what are known as max and min problems. And before we jump into multivariable functions, I want to go ahead and recall a few things from Calc 1, since there you look at max and min problems as well, right? So let's say we have a function of a single variable f, and it's defined on this closed interval a to b. And I want to first just recall a few pieces of terminology, right? So we have what are known as the absolute extrema. Okay, so this makes up the absolute max and the absolute min of the function on this interval. So what's the absolute max? Well, we say that f has an absolute maximum at a point x equals c if f of c is greater than or equal to f of x for all x in the interval a to b. So put another way, we have an absolute max at x equals c if f of c is the largest possible output of the function over this entire interval. Okay, and so on this graph here, we're looking for the largest possible y value on the graph, and that happens right here. Okay, now for the absolute min, very similar, right? We have an absolute min at x equals c if f of c is less than or equal to f of x. So in other words, f of c is the smallest possible output as we let x vary over this entire interval from a to b, so that would be right here. This is the point on the graph with the smallest y value. Okay, now a similar but slightly different notion is what we refer to as local extrema. Okay, so what's a local max of a function? Well, we say that f has a local maximum at a point x equals c if f of c is greater than or equal to f of x, but now notice here, I don't say for all x over the interval a, b, I just say for all x near c. Okay, so looking at the graph here, look at this point right here. Now while it's true, right, that the y-coordinate of this point is not the smallest possible y-coordinate for our graph over this entire interval, however, if I stay local to this point's x-coordinate, right? So in other words, I don't vary very much from this point's x-coordinate. This y-coordinate is in fact the smallest y-coordinate in that little neighborhood, okay? So we refer to this point here as a local minimum of the graph. This point, likewise, this would be a local maximum. That's the largest y-coordinate in this little neighborhood around this point's x-coordinate. All right, now this point right here, which we said was the absolute max, well, it's the point with the largest y-coordinate, right, if we stay local to this point. So that would also be a local max. And now what about these endpoints here? Can those be local extrema? Well, many textbooks, including ours, takes the following convention that local extrema just can't occur at the endpoints A and B. Okay, so these points are not considered local extrema. That's really just a convention. In fact, some textbooks actually do allow for endpoints to count as local extrema. Ours doesn't, so I'm going to stick with that convention. Okay, great. So now look at this point on our graph. Notice we have a flat spot on that graph. However, this point is not a maximum or a minimum. If I move a little bit to the left of this point, the y-coordinate, right, the output of the function actually goes up. But if I move a little bit to the right, then the output, right, the y-coordinate goes down. So this is not a max or a min. I'm going to refer to this as a saddle point. Okay, now when we go into 3 dimensions, our surface at the analogous point will actually look like a horse saddle. Okay, so that's why I'm giving it this name here. But in any event, this type of point here, where the graph is flat, is not a max or min, as we just discussed. Okay, now a couple of other comments, right? We call a critical point of the function f a number where x equals c in the domain of f such that f prime of c is either 0 or f prime of c doesn't exist. And if you recall from Calc 1, key theorem on local extrema says the following. It says that if f has a local max or min at a point x equals c, and remember, local extrema can't occur at the endpoints, so c here has to be on the interior of the interval, right, so that's an open interval from a to b, then x equals c must be a critical point of f. Okay, so if we have a local extrema, it's got to happen at a critical point. So looking at this graph here, okay, notice at this local max, we have a flat spot there. F prime is 0, so this point would be a critical point. At this place where we have a local min, again, we have a flat spot. F prime is 0, so that's also a critical point. At this point right here where we have a local max, and that happens to also be an absolute max, notice I can't define the tangent line to the graph at this point because of that sharp corner. Okay, there the derivative f prime is actually not defined, so that is also a critical point. Okay, now one thing you have to be a little careful about with regards to this theorem, okay, this says if we have a local extrema, it has to occur at a critical point, but it does not say that if you have a critical point, you're necessarily at a local extrema. Okay, an illustration of that is this saddle point. Here, right, I do have a flat spot. F prime is 0, so I do have a critical point here. However, this is not a local extrema. So it's possible to have critical points that don't correspond to local maxes or mins, right? That's what I'm calling a saddle point here. But turning this around, if we have a local extrema, it has to happen at a critical point. Okay, cool. So now with all of that in mind, okay, if I want to find and classify local extrema of a function, there's essentially two steps to doing this, right? First, you want to find the critical points, because we know if we have any local extrema, by that theorem, they have to happen at the critical points. And then the idea is to test the critical points. And there's two main ways to do this. First way to do it that I'll go over is what's called the first derivative test. This is where we build what we call the first derivative diagram, right? So I go ahead and label out the critical points. So I'm labeling those as x1, x2, x3, and x4. And so at x1, right, that's where we have that sharp cusp. The first derivative is not defined, so I did note that with a little x there. And then at x2, where I have the saddle, and x3 I have a local min, and x4 I have a local max, right? Those are all flat spots, so I put a little 0 there. And then on each one of these intervals, I go ahead and just determine the sign, right, of the first derivative. Is it positive or negative on each interval? Well, from a to x1, since the function is increasing, the first derivative is positive. Then from x1, x2, first derivative is negative, so decreasing. From x2 to x3, we're decreasing. From x3 to x4, we're increasing. And then from x4 to b, we're decreasing. Okay, so then from this diagram alone, I can determine, right, the fact that at x1 I have a local max, right? I reach that peak. At x2, well, I'm decreasing, I level out, and then I decrease again. So that's a saddle. At x3, I bottom out. That's a local min. At x4, right, I max out there. That's a local max. And that gives me a full description of the local extrema. Right? Now, another way to do this, and this is going to be our main approach for multivariable functions, is to use what's called the second derivative test. Okay, so this says that if x equals c is a critical point where f prime of c is 0. So one note here, the second derivative test actually only applies to the scenario where we have a flat spot on the graph. If f prime of c is not defined, then the second derivative test is not available, because if the first derivative is not defined, the second derivative is definitely not defined. But in any event, if we are at a flat spot where f prime of c is 0, then if f double prime of c is negative, well, that tells us we're at a flat spot and our graph is concave down at c. That tells us we have a local max at c. If the second derivative is positive, well, that's telling us what? That we're at a flat spot on our graph and our graph is concave up. That says we have a local min at x equals c. And lastly, if f double prime of c is equal to 0, well, in that scenario, the test is inconclusive. That's just telling us that our graph is extremely flat. Okay, so we're at a flat spot, but if the second derivative itself is 0, that's telling us we're really, really flat. Okay, so the reason why the test is inconclusive is that, in fact, any one of these three scenarios is actually possible. We could be at a saddle point, like I've drawn here, but we actually could be at a local max or a local min. It's just that our second derivative is not sensitive enough to detect which scenario we're in. So there we just have to do something else. All right, well, that's a good place to stop. This is just a good reminder of some of the key terms you know from Calc 1, and we'll see how this all generalizes to multivariable functions in the next couple videos. See you there.